I am Mariulagan, Associate Professor, Department of Mechanical Engineering. I am working in Konganadu College of Engineering Technology. In this college located in Tottiyam. So today we are going to see the Thermal Engineering 1 subject. So this is a Anna University 2017 regulation. So we are going to see the topic is Otto Cycle. So in this Otto Cycle we are going to see one problem. So before that we are going to read this problem. So it is cycle is constant volume cycle, or we are named as Otto cycle. Okay, so in this problem, in an ideal constant volume cycle, the pressure and temperature and volume is given for beginning of the cycle. It is the beginning means there is a initial conditions, that is a P1, T2 and V1. Okay, so the initial condition where they are given P1, and there is a pressure at the initial condition, that is a P1, and a T1 and volume at the initial condition. Okay, there is a next one at the end of the compression stroke. So pressure 12 bar. So end of the compression stroke means there is a P2. Okay, so next 315 kilojoule of heat is added per kg of gas during the constant volume heat process. Okay, so in the constant volume process we are giving the heat addition, okay, or heat supplied. Okay, so in this problem we are going to finding the value of pressure, temperature and volume at all points. Okay, so all points means the four process having the two volume process and two isometric process, isometric compression, isometric expansion process. Okay, and also we are finding the value of air standard efficiency and the mean effective pressures. Okay, first we are going to write the given data. So initial condition, there is a P1, T1 and V1 is given. So corresponding value we are to writing the first one. So next thing, there is a pressure 2, it is at 12 bar. So whenever we are going to giving the value of in the formulas, so there is a kilonewton per meter square. So and also in addition we are giving the heat supplied in the circle of constant volume process. So next thing, one by one we are going to say finding the value of temperature and the pressures for the all the nodal points. Okay, so first we are considering the process of 1 to 2. In this 1 to 2 process, the adiabatic compression process. Okay, this is the initial condition, initial process. So first starting process, the piston will be go to the BDC to TDC. Okay, so in this process they are having the compression process. So in the compression process, pressure will be increased and also temperature also increased. Okay, so the pressure and temperature directionally proportional. Whenever the pressure will increase and also temperature also increase, that same. Okay, so in the first case we are taking the thermodynamic relation, that is the P1 divided by P2 equal to V2 divided by V1 power of gamma. Okay, so in this relation we are finding the value of V2. Okay, so P1 P2 already is given for our problem. Okay, so this is the air, so this is the air standard cycle. So it's a gamma value 1.4. So and V1 is given by 0.5 meter cube. So all the values known. So we are calculating the value of V2, that is a 0.097 meter cube. Okay, that is equal to the V3. Okay, so why we are going the V2 equal to V3? There is a V2 and V3 is the constant volume process. Okay, so there is the V2 equal to V3. Okay, That's why we are we are finding the value of V2 equal to V3. There is a 0.095 meter cube. So next we are going to find the value of T2. So there is same case, we are taking the ratio is temperature and pressures. Okay, temperature and pressure relation. There is a T2 divided by T1 equal to P2 divided by P1, power of gamma minus 1 divided by gamma. Okay, so in this relation using, we are finding the value of T2. Okay, so suppose we are taking the formula T2 equal to P2 divided by P1 power of gamma minus 1 divided by gamma into T1. So in this formula we know the values pressure and temperatures and also gamma value. Okay, so we are calculating the value of T2 594.66 Kelvin. Okay, this is shows the PV diagram. There is a T is a 1 to 2 process is the adiabatic compression. So 3 to 4 is the adiabatic expansion process. So 1 to 4 and 2 to 3 is the constant volume process. So corresponding they are drawing TS diagram. Okay. So next we are going to find the T3 value. Okay. So T3 is the peak temperature of the cycle. Okay. So heat supplied during the 2 to 3 process. So heat supplied equal to mcv into T3 minus T2. Okay. So in this formula we are using the we are finding the value of T3 value. Okay. So already given the values, the Q heat supplied is given, and m is the unit mass, and CV value is a 0.718. It is a constant value. Okay, and T3 is the unknown value. Okay, T2 this already we are finding that process 1 2 to 3 using, we are find the value of T2. Okay, this value is 594.66. Okay, so here they are find the value of T3 is a 1033.38 Kelvin. Okay, so next we are going to find the value is P3. Okay, so here is how to find. So within the P3 is under the process is P2 to P3. Okay, so the P2 to means P3 means we are consider the process 2 to 3 process. This is the 2 to 3 process the constant volume process. Okay, so constant volume process. So in this constant volume process, the relation we are using pressure and temperature P2 divided by T2, P3 divided by T3. Okay, P3 this you are forming the formula is P3 equal to P2 into T3 divided by T2. Okay, so temperature T3 and T2 is known, and also P2 is known. Okay, so finally we are finding the value is P3. Okay, 2085.32 kilonewton per meter square. Okay, so next process is the adiabatic process. So in this adiabatic process is the 3 to 4 process. Okay, 3 to 4 process is the heat sorry expansion process. Okay, the expansion process we are considering the pressure and the volume relation. Okay, pressure and the volume relation using, we are find the value is pressure 4. Okay, pressure 4 means it is the end of the cycle. Okay, so end of the cycle, what is the pressure? Okay, so in the pressure is 209.94. Okay, so suppose compared to P3 and P4, the P4 will be minimum compared to P3. Okay, so because of so in the cycle end of the cycle, the pressure and the temperature will be reduced. Okay, so this is next one we are finding the value, the same nodal point, that is a temperature T4. Okay, So we are taking the relation temperature and pressure. T4 divided by T3 equal to P4 divided by P3 power of gamma minus 1 divided by gamma. Okay, so here the formula we are modified. Our finding the value is T4 equal to P4 divided by P3 power of gamma minus 1 divided by gamma into T3. Okay, so here there's a value P3 and P4 is known, and also T3 is known. Okay, finally we can getting the temperature at the T4, that is the end of the cycle. So temperature is 536.27 Kelvin. Okay, so next slide we are going to find the final solution. All the nodal point temperature pressure already we are finded, and then finally air standard efficiency and mean effective pressure we are going to solve. In this air standard efficiency, our formula is efficiency equal to 1 minus 1 divided by compression ratio R power R minus 1. Okay, so compression ratio is V1 divided by V2. Okay, so initially V1 and V2, that means of nodal point 1 to 2 is the compression process, adiabatic compression already we are said. Okay, so the compression process R equal to V1 divided by V2, that value is V1 0.5 and V2 0.097. Okay, so we are in this value we are summed, or is there R value is 5.16. Okay, so putting the values in the efficiency formula. Okay, so 1 minus 1 divided by 5.16 power of gamma value is 1.4 minus 1. Okay, so our cycle efficiency is 48.13 percentage. Okay, so next we are going to find the value is pressure ratio. Okay, so in this pressure ratio notation is K. Okay, K equal to P3 divided by P2. So the P3 is the 2085.32 and P2 value is the 1200. So finally we are getting the pressure ratio 1.74. Next to last one we are going to find the values mean effective pressure. Okay, so we need the mean effective pressure formula. So having the P1 and the R means is the compression ratio, K is the pressure ratio, and gamma value is known 1.4. Okay, so in this formula we know the all the value finded, and also we can finally finding the value is mean effective pressure. Okay, so what is a P1? 1.4. Compression ratio is 5.6. Pressure ratio already we are finding the values 1.4 minus 1 divided by gamma value 1.4 minus 1. Okay, so next we multiply it to the compression ratio 5.16 power of 1.4 minus 1 divided by 5.16 minus 1. This for equal to the value is mean effective pressure 2.56 bar. Okay, so in this form problem we are final find the value is mean effective pressure. So thank you for watching this form problem. Okay, next video we are see the another problem. Okay, thank you.